Hello, compiler fans! Today, let's unravel 3 address code, or TAC. When you write code like x equals sign a plus b asterisk c, the computer doesn't just get it, the compiler translates it. A compiler acts as a translator, turning your high-level code into something the machine understands. But it doesn't do this in one step. It uses an intermediate language. TAC is one of the most popular. TAC breaks complex statements into simple steps, each with at most 3 addresses, a result, and up to 2 operands. For example, x equals sign a plus b asterisk c becomes a series of simple instructions, each easy for the compiler to process. TAC sits between the front end, which reads your code, and the back end, which generates machine code, making the process modular and efficient. Without TAC, every language would need a separate compiler for every machine, an impossible task. With TAC, you only need to translate to and from this universal format. This divide-and-conquer approach is why compilers are so powerful. Let's see how TAC actually works. Let's break down a line of code x equals sign a plus b asterisk c, d. TAC makes the order of operations explicit by splitting it into simple steps. First, multiply t1 equals sign b asterisk c. Next, add t2 equals sign a plus t1. Finally, subtract x equals sign t2, d. Each instruction is clear, one operation at a time, no ambiguity. This step-by-step format is perfect for machines and makes optimization easier. TAC isn't just for arithmetic. It handles assignments, control flow, and jumps too. For example, if x, y go to L1 or go to L2, this lets TAC represent any program's logic in a simple, linear way. By breaking code into these atomic steps, compilers can analyze and optimize efficiently. That's the power of TAC. Now let's see how it's stored. TAC instructions are often stored as quadruples, structures with 4 fields: operator, argument 1, argument 2, and result. Think of each instruction as a row in a table. For our example, row 0, multiply BC T1, row 1, add AT1 T2, row 2, subtract T2 DX. Each result can be used in later instructions, making data flow clear. Quadruples make code easy to optimize. Moving or changing instructions is straightforward. The explicit naming of temporaries helps track values. The trade-off? Slightly more memory to store all those names. But for most compilers, the clarity and optimization benefits are worth it. There's an even more compact way. Let's check it out. Enter triples, a more compact way to store TAC. Triples use 3 fields: operator, argument 1, argument 2. No explicit result name. Instead, results are referenced by their instruction index. For our example, 0, multiply, b, c, 1, add a, 0, 2, subtract, 1, d, 3, assign, 2, x. This saves memory by skipping temporary names. The downside? Moving instructions during optimization is trickier, since references must be updated. Triples are efficient, but less flexible for code changes. So, which is better? Quadruples versus triples. Each has strengths. Quadruples use explicit temporary names, making data flow and optimization easy, but use more memory. Triples save space by referencing results by index, but make optimization more complex. For optimization, quadruples are preferred. You can move instructions easily, and names keep everything connected. For memory savings, triples win. No need to store all those temporary names. The choice depends on the compiler's goals, speed and optimization, or compactness. Most modern compilers favor quadruples for their clarity and optimization power, but both approaches are vital tools in compiler design. Understanding the trade-offs helps you appreciate how compilers work under the hood. Let's wrap up with why this matters to you. On to the finale. Why should you care about TAC, quadruples, and triples? Knowing how your code is transformed helps you write better, faster programs. Compilers use TAC to optimize, moving calculations, removing unused variables, and more. These optimizations make your code run faster and use less memory. If you ever design a language or debug performance issues, understanding TAC is essential. Quadruples and triples are the backbone of this process. TAC bridges your high-level code and the machine's instructions. By understanding this layer, you gain insight into the science powering modern computing. It's not just theory, it's what brings your code to life. Thanks for joining this journey into the heart of compilers.